Digitizing information is simply using the Arabic number symbols 0 through 9 to represent some form of information. Humans have digitized information long before the development of computers, such as social security numbers, employee numbers, telephone numbers. These are all examples of digitization. Of course, digits are also used to represent quantities, such as checking account balances and prices and distances, etc. When digits are used to represent information that is not quantifiable, such as a telephone number, then digits are not inherently better symbols to use than some other set of symbols. On the other hand, digits symbols are often used because they have short, well-known names, 0, 1, 2, 3, 4, so they're easier when you're calling them out. Here's an example of 3 telephone keypads with different symbols. Now, my office phone number is 7623124, but we could give the call out for my phone number using an alternate set of symbols, such as this one, where I would do an and caret at pound bang at $, which represents the exact same buttons on this keypad to call a particular phone number that would go to my office. Another motivation for using digits to encode information is the universal understanding of the collating sequence of digits. 2 comes before 3, but after 1, and so on. If some other symbols are used to represent information, then a collating sequence would need to be established if the information is to be placed in some numerical order. This illustrates that when you're choosing symbols for the purpose of encoding information, you should really consider how the symbols interact with the information being represented. When the physical world and the logical world meet, a fundamental pattern of information representation occurs. This is known as the presence and absence of phenomenon. For example, is light detected at a specific place and time? Is sound detected at a specific place and time? We're not representing the amounts at this level of information, but whether it simply is present or it is not. In the logical world of information technology, the use of true and false are used to represent the presence or absence of a phenomenon. This is done by associating true with the presence of a phenomenon and false with its absence. This type of representation is referred to as a panda representation, PNA or panda. So panda will be the mnemonic we'll use to remember the representation of some physical thing. But it's important to understand that physical phenomena such as sound waves are continuous, but panda representations are discrete, meaning separable or distinct. This is because you cannot represent a continuous signal such as a sound wave in the same way in a computer as it exists in the physical world. So now we can use any number of different terms to name the panda pattern. For example, we could call it true, false, or 1, 0, on, off, yes, no, plus, minus, etc. The use of these two patterns of a form a binary system, and the units are called binary digits. The contraction is bit. It's important to understand that when you are using a bit, it can only be encoded with a value of 1 or 0, which represents the presence or absence of some phenomenon. So a single bit cannot represent more than 2 things. To represent or encode more than 2 things, it is common to group bits together, which is into what is called a byte, 8-bit bytes. Again, Since a bit only has a value of 1 or 0, a single bit alone can only represent symbolic things like stop, go, up, down, yes, no. Grouping bit values into sequences allows us to represent more than just two symbols, like one loss. We can encode complex information using one sequence of zeros and ones for each symbol. How many symbols we can represent with a sequence depends on how long the sequence is. The basic rule is that a sequence is n bits will allow you to represent 2 to the n symbols. For example, a sequence of 4 binary bits, or 2 to the 4th, will allow you to represent up to 16 different symbols. If we have 7 binary bits, that's 2 to the 7th, and that allows us to represent up to 128 different symbols. The author wants us to understand the concept behind this and uses the analogy of a sidewalk where each square of the concrete is a bit. We're told that where a stone is placed on a square, it corresponds to a bit value of 1, and the absence of a stone in the square corresponds to a 0. So in this example, we have the presence of a stone, absence of a stone, presence of a stone, absence, 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 presence, and absence. What this represents then is the binary sequence 1 0 1 0 0 0 1 0. Now, what can we do with something like that? Well, this example or this table shows the analogy with a 4-bit sequence, which can be used to represent any of the 16 symbols of the hexadecimal numbering system. For example, the binary pattern of 0 1 0 0, representing absence, presence, absence, absence of our stones on the sidewalk, represents a hexadecimal value of 4. Whereas a pattern of 1 0 1 0, presence, absence, represents a hexadecimal value of A. Hexadecimal is a base 16 system that starts out like the symbols of the decimal numbering system, going from 0 to 9, but uses the letters A, B, C, D, E, and F to finish the last 6 of the 16-digit symbols of the system. It is a numbering system that helps us work with computers, and the concept is that programmers need to work between what humans like as a numbering system, which is decimal, and what the computer likes as a numbering system, which is binary. And so hexadecimal is used so that you can avoid making errors while working with computers. So as you see, the use of different numbering systems is an important part of working with information technology, and the understanding of how to convert numbers in one system to another system is an essential skill. This table shows a relationship between decimal, hexadecimal, and the binary number systems. But to have a thorough understanding of the conversion process, we need to practice an algorithm that will convert from one number system to another. For example, converting decimal numbers to a binary number. Since binary bits which have a value of 0 or 1 are usually grouped within the computer as a byte consisting of 8 bits, let's start our algorithm for converting from decimal to binary by creating 8 blanks to represent each of the bits in an 8-bit byte. Okay, next what we're going to do is, starting from the right side, the right blank, we're going to work left, showing each blank what its decimal value is. 1, 2, 4, 8, 16, 32, 64, and 128. Notice that all I did was simply doubled the value of each blank as I moved from the right to the left. Now, why are these numbers assigned to each of these blanks? Well, again, it's because binary, which literally means two parts, is a base 2 numbering system. So each blank or place value of a 8-bit binary number is using the base of 2 raised to some power starting with 0. So 2 to the 0 power is equal to a decimal 1. 2 to the 1 power is equal to a decimal 2. 2 to the second power is equal to a decimal 4. So on until we get to 2 to the 7th power, which is the last place value in the binary number, and 2 to the 7th power is equal to a value of 128. It's not important that you actually understand this whole concept of base 2 being raised to a power. Really all it matters is that you remember that starting from the right, you have a 1, and then double it to be a 2, double it to be a 4. For the next place value, it's an 8, a 16, a 32, a 64, 128. And this, of course, is for an 8-bit binary number referred to as a byte. So let's go ahead and make a conversion here. We want to convert the decimal number of 114. So what we're going to do is simply ask the question, starting with the largest number in our pattern, which is 128, can we subtract 128 from 114? In this case, we can't have negative numbers, so the answer is no. So we place a 0 in the place value for 128 of our binary number. Next, we ask the question, will 64 go into 114? Yes, we can subtract 64. So we place a 1 in bit 64, and we subtract 64 from our 114 value. We end up with a value of 50. The next place value in the binary number is 32. Can we subtract 32 from what's left? Yes, we can. 32 from 50 is going to be 18. So we placed a 1 in the 32 spot. We subtracted 32 from 50. Now we have 18. We ask the question, does 16 go into 18? No. So we place a 0. I'm sorry, yes. So we place a 1 in the 16th place, and we subtract 16 from 18. We get a value of 2. So continuing on, will 8 go into 2? No. So we put a 0 in the 8th spot. Will 4 go into 2? No. So we put a 0 in the 4th spot. And then finally, will 2 go into 2? And the answer, of course, is yes. We subtract 2 from 2. We get a value of 0. And our last place value is 1. Can we subtract 1 from 0? No. So we place a 0 in that location. So at the end, when we've converted 114 to binary, we have a pattern of reading from the right to the left, the left to the right, 0, 1, 1, 1, 0, 0, 1, 0. So let's try this one more time. Let's convert the number. Well, let's start off by putting in our blanks, 1, 2, 3, 4, 5, 6, 7, and 8. And then put the place value for each blank, 1, 2, 4, 8, 16, 32, 64, and 128. And let's convert the number of decimal 54. So again, we start off asking the question, will 128 go into 54? No. So we place a 0 in that place value of the binary number. Will 64 go into 54? Of course, no. So we place a 0 into its place value. Will 32? Yes. So we subtract 32 from 54, and we get a value of 22. Can we subtract 16? Yes. So we place a 1 in the 16's place, and we subtract 16 from 22. 8 cannot be subtracted from the remainder. That's 6. So we place a 0 in its location. 4 can be, so we place a 1 and subtract 4 from 6 to get 2. And then 2 can be subtracted from 2, so we place a 1 in the 2's place, subtract 2, we end up with a value of 0. 1 cannot be subtracted from 0, so we place a 0 in the ones place. So converting the decimal value of 54 to binary, we end up with a pattern of 0, 0, 1, 1, 0, 1, 1, 0. So we've seen that Panda patterns like binary can encode numbers like decimal and hexadecimal. Another early computer use of binary, which is still used today, is to encode keyboard characters. While this was and still is an important use of binary, representing sound, images, video, and other types of information are equally important. So let's take a look at the keyboard. There are 26 uppercase and 26 lowercase Roman numerals, 10 Arabic symbols, 10 arithmetic characters, 20 punctuation characters including space, and 3 non-printable characters like new line, tab, and backspace. That gives us 95 characters. We need to have a sequence of binary bits that will allow us to encode at least 95 characters then. We can't use a sequence of 6 binary digits because that will only allow us to encode up to 64 different symbols. So we ended up with 2 to the 7th or a 7-bit sequence, which would allow us to encode up to 128, more than the 95 characters that we need to represent the English language. This is called the American Standard Code for Information Interchange, and it was an early standard that is still in use today. The 7 bits that we use by the 1960s, it's clear that this is not going to work because it was developed in the United States, only had enough bits to encode for the English language. So IBM, who was the dominant world manufacturer at the time for computers, added an 8th bit to represent other Western European languages, and it initially was referred to as extended ASCII, but it allowed for 256 different symbols, which would make room for all of the Western languages, Latin-based languages. This is the standard ASCII table then that we use even today to encode the characters from the keyboard. So let's take a look at how to read this. For example, if we were encoding the character lowercase m, the way we read this table is we start off by reading the 4-bit binary sequence of the row that the m appears in on the table. So that would be 0, 1, 1, 0. And then we find the column that the letter is in, the table, and we read from the top down 1, 1, 0, 1. So the entire 8-bit ASCII sequence for a lowercase m is 0, 1, 1, 0, 1, 1, 0, 1. You're going to need to know how to read this table to do one of the homework assignments that is coming up. I'm going to give you an encrypted message that you have to convert from 8-bit binary that represents ASCII sequences to figure out what the letters are in the message. By the 21st century, of course, we realized that even the 8-bit binary pattern of ASCII was limited in terms of representing only Latin-based languages in Europe. And so we needed to see an expansion to something called Unicode. And Unicode is a 16-bit representation. It's compatible with 8-bit ASCII in that all of the lower 256 characters that are in the Unicode are equivalent to the 256 characters from the ASCII table. But the additional characters that we can encode, since now we can go up to 65,000 characters, allows us to represent all sorts of scripts besides Latin-based ones. A very important concept at this point to explain is that when we are encoding information, especially numeric information, there are now two different ways that we can represent something like a telephone number. In this example, we've got the telephone number 888-555-1212. When we look at the representation of that, we can say we have an 8-bit representation of the character 8 from the keyboard, and this is very much different than the numeric value of 8 that could also be represented by a binary sequence. So it's important that we understand when we're looking at a binary sequence, in this case 8 bits, that we recognize what the context of the information being encoded is. So in summary, digitizing does not require digits. Any number of different symbol systems could be used. Panda encoding is creating patterns based on the presence and absence of physical phenomenon, the two states of a bit or a binary digit. Bit states are often represented as 0 and 1, but can actually have any two opposite terms like plus, minus, yes, no, etc. 7-bit ASCII is an early assignment of bit sequence symbols to encode keyboard characters. It was quickly extended to 8-bit ASCII so that it could encompass the encoding of more than just the English language. 8-bit patterns for numbers can represent the quantity of 8 or the keyboard character of 8 and will not be the same pattern. As a rule, 8-bit patterns must have their context identified before we know what they are actually encoding. And finally, for trivial pursuit, byte was historically spelled with a Y to avoid confusion with the word bit.